Welcome to the first in what I hope is a series of no-frill podcasts on organic chemistry. I'm Dr. Brian Lloyd, and what you see before you is a whiteboard on which I will be writing a series of lectures, or what I like to call scribblecasts, dealing with topics in organic chemistry. These will be supplements to what you cover in class, and hopefully you will find them useful. This first one is the first part in a two-part series on atomic structure. Atomic structure is very important to the organic chemist because organic chemistry involves a study of chemical reactions in organic molecules, the making and breaking of bonds, and understanding chemical structure of organic molecules, or the bonding between atoms. And bonds are controlled by electrons. To understand the electron, one must understand the atom. So let us begin by looking first at the nucleus. If I draw a nucleus, we know the fundamental particles that exist inside the nucleus are the neutron and proton. The neutron has no charge. The proton has a positive charge. Let me fix that. A positive charge for protons. Out in the space surrounding the nucleus, we find the electron. The electron is negatively charged. Now, in the classical model, the electron can exist anywhere near the nucleus, but in the quantum mechanical model, the electron is quantized or limited to discrete energy levels, and we're going to talk a little more about this. Let's begin by a quick look at the nature of the nucleus. If we were to relate this atomic structure to the elements of a periodic table, say this element symbol E. To be element E, there must be a certain number of protons. The number of protons determines the nature of the element. And so, the atomic number we find in the periodic table simply is the number of protons. A, the atomic number, is often written as a subscript before the element symbol. The number of neutrons can actually vary. A superscript value, called mass number, is placed on the element symbol as well. The mass number represents the sum of neutrons and protons. So if we wish to determine the number of neutrons, we simply take the mass number and subtract the atomic number from it. Let's look at an example. If we look at the element chlorine, chlorine has 17 protons. To be chlorine, you must have 17 protons. Change the number of protons and you're not a chlorine atom. Now, one example of a chlorine is an atom with a mass number of 35, referred to as chlorine 35. Chlorine 35 has 18 neutrons. The sum of the protons and neutrons equals the mass number. It turns out that chlorine 35 has a natural abundance of 75.5%. That natural abundance simply means that if you took a compound that had chlorine in it, like table salt, sodium chloride for example, 75.5% of all sodium chloride would have chlorine 35. What's the other 24.5%? Well, it is chlorine. So it has 17 protons, but in this case it is chlorine 37. Chlorine 37 has a natural abundance of 24.5%. So if I look at a sample of table salt, 75.5% of the sodium chloride molecules in table salt would have chlorine 35. 24.5% of the sodium chloride would be chlorine 37. Now, these represent the naturally occurring isotopes of chlorine. But there are other possible isotopes. For example, chlorine-32 is a radioactive isotope that has a half-life of 0.31 seconds. When I say it has a half-life of 0.31 seconds, I mean that is the amount of time it takes for half of the sample to decay into another form of nuclei, radioactive or non-radioactive. Chlorine-31 has a half-life of 2.5 seconds. Chlorine-34 has a half-life of 6.56 seconds. And so that you don't think everything's short-lived, chlorine-36 has a half-life of 310,000 years. Now that's all I'm going to say in the short term about the nucleus, because what we're really interested in as organic chemists are the electrons. The electrons are what determine the nature of bonding in organic molecules, and that is what is very important in chemical reactions and reactivity. So let us take a look now at the nature of the electron. If I were to consider the electron around the nucleus of the atom, I would be able to describe those electrons in terms of energy. And I could rank them in terms of energy. Now, the energy levels I'm going to discuss are referred to as shells. And they're given the symbol N, and they're referred to numerically as N equals 1, 2, 3, 4, and 5. So N equals 1, 2, 3, 4, and 5. Now these shells have been sometimes, in the past, been sometimes referred to by an alpha symbol, such as K for 1, L for 2, M for 3, and so on. This KLM nomenclature I only mention because you might run across it in surface science studies. You might hear expressions such as the ejection of a K-shell electron. But having said that, that's all we're going to do. And we're going to refer back to this numerical methodology. Now, when we describe the shells in which the electrons lie, we describe the electron as being quantized, which means it exists in discrete energy levels. As soon as you start using a terminology like this, you tend to lose the student. They get confused. So sometimes it is nice to use an analogy to show students that really you have a good grasp of quantization. And the analogy we're going to use is humans existing in an apartment building. So I am now drawing, believe it or not, an apartment building. I hope it looks like an apartment building when I'm done. And here is my apartment building. Now, if I was to try and describe the location of humans in an apartment building, one requires an understanding of the structure of the apartment building. It's not sufficient to know that there's just a rectangular cube there. We want to know the nature of the inside structure of the apartment building itself. And one of the first things we know about apartment buildings is that they are divided into floors. So I can draw these floors. And just like apartment buildings are subdivided into floors, the energy levels the electron finds itself in are divided into shells. Now, the analogy works really quite well because one knows that Humans can live on the first floor, or the second floor, or the third floor, or the fourth floor, but they can't live in between these floors. You can't live on floor 2.5. In that sense, we could almost say that the human beings in an apartment building are quantized. That is, they live on discrete levels. And you're totally comfortable with that. I don't think anyone's confused about it. Well, when we say the electrons in the shells are quantized, what we're saying is you can either be on level 1 or level 2, but you can't be between that. And so in many ways, it's like the floors in an apartment building. Well, is it sufficient to say that when I come to my apartment building, if I want to know where a person is, that they're on the first floor? Well, we know that's not sufficient because floors are subdivided into apartments. All right. How does that relate to the electron model? Well, in actual fact, it turns out shells are also subdivided. And they are subdivided into subshells. Now, in the apartment building, one could ask, well, how many apartments are on a floor? Well, that very much depends on the size of the floor. It depends on the size of the apartment building. Same question we ask about our subshells. Shells. How many subshells does each shell give us? And fortunately, there's a very simple numerical relationship. The value of n determines the number of subshells you get. So n equals 1 can only have one subshell. N equals 2 can have 2 subshells. N equals 3 can have 3 subshells. N equals 4 can have 4 subshells. And so on. Now all we need is to give the subshell a designation. Chemists have chosen a unique lettering system for the subshells. They started with the lowest energy or first subshell with the letter S. This is then followed by the letter P. And as you increase in energy, letter D, and then the letter F. After letter F, it follows the normal alphabet, G and H. So the n equals 1 shell can be subdivided into a subshell called the 1s. And it only has the one subshell. The n equals 2 shell can be subdivided into 2 subshells, a 2s and a 2p. Let's do the third one over here. So I'm going to draw a nice curve over here. And we'll do the third one starting here. The n equals 3, I told you, could be subdivided into 3 subshells. What are they? The 3s, the 3p, and the 3d. I'm going to have to go up here for the fourth. The n equals 4 shell can be subdivided into 4 subshells. The 4s, the 4p, the 4d, and the 4f. All right. So there you have it. The electron exists in shells, and these shells can be subdivided into subshells. Shells are similar in an analogy to floors, where subshells are like the apartments in an apartment building. Now, if we go back to our analogy of the apartment building, is it sufficient if you wish to know the precise location of an individual to know what floor they're on and what apartment they're in? Well, the answer is no. Apartments come in a variety of sizes and shapes. Some apartments are single rooms, but some apartments can be suites that have many rooms in them. And if you really want to know the location of an individual in an apartment building, you have to know what floor they're on, what apartment they're in, and what room they're in. So apartments can be subdivided into rooms. Well, just like subshells are represented by apartments, the rooms of the apartment building represent what subshells can be subdivided into. So just like an apartment building can be subdivided into floors and apartments, and then the apartments divided into rooms, subshells can be subdivided into what are called orbitals. So here we have it, orbitals. What are orbitals? Well, that takes a little explanation. What is an orbital? An orbital is a region of space around the nucleus of an atom. A region of space around the nucleus of an atom. And this is the most important part, where there is a chance of finding an electron. So, orbitals are defined as a region of space where there is a chance of finding the electron. Why not the exact position? What's this nonsense about a chance? Don't we want to know where the electron is? Well, if I'm going to stay simplistic about it, suffice to say that the error in the determination of the position of the electron is about the size of the atom itself. And what that means is you can never know the precise position of an electron. When you discuss this topic, all you can talk about is probabilities of finding an electron. And so when we draw orbitals, we often draw them in terms of 95% probability, 99% probability. And this leads to orbital shapes that are regions of space surrounding the nucleus at very tiny distances. And we're talking about in angstrom. So now, if you say, well, what if we want to know where there's a 100% chance of finding an electron? If you plug 100% probability into the equations quickly explode, and you start getting numbers that are infinite in size. And this suggests if you want to know where there's a 100% chance of an electron, well, there's a chance of finding the electrons in the atoms in your body outside of our solar system. Now, that chance is extremely small, because as soon as you put in 95% or 99%, it shrinks way down to the size of an atom. Okay. So orbitals are defined as a region of space where there's a chance of finding the electron. Well, apartments are subdivided in a various number of rooms. How many orbitals do we divide the subshells into? Well, it turns out, now I'm going to symbolize our orbital with a straight line on which we can draw electrons. Okay, so I'm going to symbolize an orbital just as a straight line. Turns out the S subshell can be divided into one orbital. So every S can have one orbital. And you'll notice a pattern developing as we proceed. The P, the next subshell, can be divided into three orbitals. So here's my P. The D can be subdivided into 5 orbitals. And the F can be subdivided into 7 orbitals. Now you should begin to see the pattern if you look carefully enough. 6, 7. What have we done here? We started with 1, 3, 5, 7. We're increasing by 2 every time. If I look at the fifth shell can have 5 subshells. The 5s, the 5p, the 5d, the 5f, and I said after f we follow the normal alphabet, the 5g. I could ask you, how many orbitals does a 5g subshell have? Well, if we follow a pattern, 1, 3, 5, 7, what do we get? 9. There are 9 orbitals in a 5g subshell. Okay. So there it is. The orbital is the region of space where there's a chance of finding the electron. There remains only one thing to do, and that is to put the electrons in the orbital. But how do we do that? How many electrons can fill an orbital? Are there any restrictions on how they fill an orbital? Some of this we're going to leave to the second part of the atomic structures podcast. But in this section, there are some analogous rules we can use to reveal the nature of filling these orbitals with electrons. The first is in the human apartment building. The first rule to remember is two's company, three's a crowd. You never put more than 2 electrons in an orbital. You can place just 1, but no more than 2. The second rule in the apartment building is that opposites attract, and hence the electrons going in the orbital must be of opposite spin. So what we're coming up here is a rule on how to fill orbitals, and we will name this rule in the next podcast, but you can never put more than 2 electrons in any one orbital, and they must be of opposite spin. So I'm going to represent my electron as an arrow. The arrow represents the spin, so if I put a second electron, I must represent it as opposite spin. And I would fill it this way. So if I was filling the Ds, I would draw in my electrons thusly. And you'll notice, because there are 5 orbitals in the 4D subshell, I can put 2 electrons in every orbital, or a total of 10 electrons in the 4D subshell. Okay, now there you have it. What if I want to take my analogy further? What if I want to create a fictional apartment building for electrons? What would it look like? Well, I can take this fictional analogy and create, for a visual that might help me remember this, a drawing of what the electron apartment building might look like. So I'll draw. Clearly, the lowest energy level only has 1 subshell, and if space, if we use the amount of room on the floor, what have I just drawn? Well, what I've drawn looks like an inverted pyramid. And so if we look here on the first floor, there's only enough room for 1 apartment. As we go up on these floors, there we go. Oh, what a mess. We get more and more room. More and more space allocated to our floors. And so as you see in our electron apartment building, as we rise from the first floor to the second floor to the third floor, fourth floor, we get more and more room for more and more subshells. And that gives us room for more orbitals. Now, again, this is a total fiction. It's just an analogy. If it helps you remember why we get only 1 subshell in the first shell and then 2 in the second shell, use it. But if it doesn't help you, you can quickly forget it. Now, the next thing we do want to talk about is what these orbitals look like. It turns out that all of these orbitals are calculated from the wave functions of the electrons, and we're going to discuss this a little later on. Suffice to say that if we take the square of the wave function, we actually get the probability distribution of finding the electron. We can plot that as a map. It turns out all the s orbitals are spherical. All the s orbitals are spherical. And the only difference between the 1s and 2s is in the 2s you actually get a surface inside the sphere where there's 0% of finding an electron, and that's called a node. You don't really need to know that at this point. The p orbitals are dumbbell shaped or figure 8 shaped. You say there's 3 of them. How do they differ? Well, they differ in the location of space. This one's drawn along the y-axis. Another one would be drawn along the x-axis. And one would be coming out towards you along the z-axis. And each one of these 2 lobes would be a single 2p. One along the y, one along the x, and one along the z. When we get to D and F, we start getting weird and wonderful shapes. And they become more complicated, but we don't need to go there at this point. So there you have it. The electron exists in energy levels that are described as shells. These shells are quantized. That is, the electron only can exist in the level 1, 2, 3, or 4, not between them, much like humans existing on floors of an apartment building. Like a floors in an apartment building which can have apartments, these shells can be subdivided into subshells. The lowest energy can only have 1 subshell. N equals 2 can have 2 subshells. And this leads to the picture of the electron apartment building being much like an inverted pyramid. Just like the human apartment building, the apartments can be subdivided into rooms, while subshells, the apartments can be subdivided into orbitals, or rooms. Orbitals are regions of space where there's a chance of finding the electron. When you place electrons in the orbitals, you must place no more than 2 electrons in an orbital, and they must be of opposite spin. Note the pattern of the orbitals, that the s can only have 1 orbital, the p's can have 3, and that pattern always increases by 2. What we're going to do next lecture is we're actually going to continue with atomic structure, but describe